Good morning. Today, Daniel and I will be presenting on performance curves for individual unit operations. In this presentation, we will talk about performance curves and their applications to heat transfer, fluid flow, separation problems, and provide a summary. So what are performance curves? These are ways to represents the ways a piece of equipment responds to changes in the input or changes in the variable. And they are typically shown in graphs to make it easier to understand and see what's going on in the system. Here's an example of performance diagram for a heat exchanger. You see over here it has different values for the airflow along the x-axis and different values for the this value here is the heat duty divided by the temperature difference. And the different lines represent different sizes of rotors for the fans in the system. And each one has its own performance, which is the airflow increases, the heat duty divided by the internal temperature difference increases. This is just an example of one type of performance diagram. Some of these applications to heat transfer, you can have different changing variables. Some of these include temperature, flow rates, heat transfer area, and heat duty. And for the performance curve, you can hold some of these constant while changing others and generate different curves depending on what you're looking at changing in your system to see how the unit will respond to those changes. And fouling is the accumulation of material on surfaces over time. And this will decrease the performance of a unit, and this is especially problematic for units involving liquid flow. And performance curves and how they apply to fluid flow. So once again, some changing variables for fluid flows are the flow rates, the pressure, also called the fluid head, pipe diameter, and the impeller size. And just like I mentioned with heat transfer, you can keep some of these constant and change others and see how the system responds to those changes. For fluid systems, you have pump limitations. An important limitation here is the net positive suction head, or NPSH. And this is the minimum pressure within the pump. This actually causes the liquid to vaporize because of the low pressure, and this creates cavitation, which is just air bubbles inside your pipe or your system. And you don't want to have cavitation, it will damage your unit. So you want to avoid that at all costs. And there are ways you can increase the acceptable NPSH region. Some of these ways include decreasing the temperature of the liquid at the inlet of the pump. You can increase the diameter of the pipe entering the pump, or you can increase the pressure. This is why a lot of pumps are at a lower elevation than the fluid that is coming into them. Here's an example of an MPSH curve. Bottom on the x-axis here, you have gallons per minute, your flow rate. On the y-axis, you have your total head or your pressure in feet. And it's a little hard to see, but these lines coming down here are the MPSH curves. And what they tell you is the minimum amount of pressure that you have to avoid cavitation for a certain diameter of pipe. So say you wanted to run a 250, you want to have a flow rate of 250 gallons per minute in a 10-inch diameter pipe. You would go to 200 on this line and come across on the 10-inch line. You would see that you would need at least a 4-inch pressure to avoid cavitation. Now I'll let Daniel talk about compressors.
So, compressors work a lot like centrifugal pumps, and their curves are very similar. They're read the same way. These curves are supplied by the manufacturer, and a notable feature on this curve is the surge line. if you see that diagonal surge line right there, it represents the peak of that curve, and if you go to the left side, you're in danger of damaging your equipment, because what will happen is as that curve starts to decrease, the pressure will decrease inside your system and you'll get backflow, which can severely damage your pump. So as a safety measure, you stay to the right side of the surge. When talking about separation, there's a few different units used. Tower columns as well as pack towers are both effective at separating different materials, so you have to choose it based on what materials you're trying to separate. More stages or a taller column with theoretical stages will result in better separation. So on the right here, you've got a qualitative relationship displayed in a graph. And the equations you can see better in the book, but the equations on the y-axis determine, that's what you're trying to find when you have your parameters, you look on the different lines, you find how well it's going to separate it given your different column qualities. There's no closed form relationships when dealing with columns like this, so you're not allowed, you're not going to be able to find an equation that perfectly describes your system, so you're going to have to go with the qualitative relationships. Type of separation processes that we know a lot about, or quite a bit from distillation course, is distillation. And I'm sure you've all remember the McCobb-Thiele diagram, where on the x and y axis, you've got your compositions, and as you're trying to separate it, you're going to step down the column stages in that graph. And we're pretty experienced in that. What we haven't seen so much is the performance curve of a distillation column. That's down here on the left side. Each of these has to be crafted to the specific column with the number of stages it has and where the feed is placed and what you want as exit compositions. These aren't supplied by the manufacturer, nor are they qualitative relationships that you can just find easily. Each of these has to be crafted to your specific situation. In summary, performance diagrams are important. They help you know a lot about your system, and they can be provided by the manufacturer or universal curves that are described by equations with specific assumptions that go with those equations to help you know something about your system. In other cases, like heat exchangers and distillation columns, you have to specifically apply your knowledge to define that curve yourself and work out relationships based on the behavior of the equipment. These unit ops are all important, but what is absolutely essential to regulating flow and adjusting for unforeseen changes in your system is a regulating valve. It helps you manipulate your outputs. It's inexpensive and absolutely essential to maintaining your process. Any questions?